Hey guys, we are back in chapter 10 with section 2, where we will talk about the fundamental counting principle and permutations. So, in the first section of this chapter, we saw that the key to being able to compute theoretical probabilities is being able to count up the number of outcomes in a sample space and the number of outcomes that make up certain events. When, when a sample space is small, like the outcomes for rolling a die, you can literally list and count them. But as probability experiments get more complicated, we're going to need to learn some techniques that go beyond simply listing and counting. And that's where the fundamental counting principle comes in. So in a sequence of n procedures, if the first can occur in K1 ways, the second in K2 ways, the third in K3 ways, and so on, the total number of ways the sequence of procedures can occur is here. In other words, you're just going to multiply the total number of ways, each one, you're going to multiply each number to come up with the total of number of ways that the sequence can occur. So the occurrence in the first event in no way affects the occurrence of the second event, which in turn does not affect the occurrence of the third event, etc. So when we see the example, it'll make more sense. But each of these is the number of ways that event can occur. So let's look at our very first example. There are 4 basic blood types represented by letters A, B, AB, and O. There is also an RH factor represented by either positive or negative. If a local blood bank labels donations according to RH factor and gender, according to type, RH factor, and gender, I'm missing one, of the donor, how many different ways can a blood sample be labeled? Okay, well, blood type, we have 4. 1, 2, 3, 4. Our H factors, we have 2. 1, 2. And gender, we have 2. So if we multiply those out, 4 times 2 is 8, times 2 is 16. So in this case, we have 16 different ways that blood can be labeled. So this is what the fundamental counting principle is saying. Like we said, the first way can occur 4 ways. The second, the RH factor, can occur 2 ways, and the gender can occur 2 ways. So you multiply those out and you come up with your total. All right, let's look at our next example. Using the fundamental counting principle with repetition. So the letters A, B, C, D, and E are to be used in a 4-letter ID card. How many different cards are possible if letters are allowed to be repeated? Okay, so we are able to repeat them. A good way to start this off is to just set up an example. This is my 4-letter ID card, and I can use the letters A, B, C, D, or E on each of them. Okay, they can repeat, so those same numbers can happen each time, which means I can take 5 times 5 times 5 times 5 to figure out how many different cards are possible. Okay, 5 times 5 times 5 times 5 gives me 625 possible ways. Now the second part says how many cards are possible if each letter can only be used once. Only be used once. So we're still in the same thought process of 4 letters, or 4-letter ID card. However, the first time we have A, B, C, D, or E, that's 5. We take one away because we can't use that one again. That's 4. Take one away. That's 3. Take one away. That's 2. So 5 times 4 times 3 times 2. In this case, will give us 120 different ways. Okay, hope that makes sense. The first one, because the letters are repeated, we can use them each time. The second one, because we cannot repeat them, they are only used once, we have to take one away each time. All right, so this leads us to our next topic of factorial notation. The next couple of counting techniques we'll learn use factorial notation. The symbol for factorial is the exclamation mark. In general, n factorial means to multiply the whole numbers from n down to 1. Here's our example. If it says 1 factorial, it's just going to be 1. If it says 2 factorial, we're multiplying 2 times 1. 3 factorial, 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1. So on and so forth. So whatever factorial they're giving us, we're multiplying that number by all the numbers below it. All right, let's go ahead and look at an example. Example 3 says evaluate each expression. 8 factorial. Well, that just means 8 times 7, 6. Oh, getting ahead of myself. Times 5 times 4 times 3 times 2 times 1. Punch that in our calculator. Letter B says 12 factorial over 10 factorial. Okay, so that bar is a division bar. And we can write 12, and this is where we can write it. I can show you guys a little trick. We know 12 factorial is 12 times 11 times 10. Now, when I get to 10, I'm going to leave that at factorial because that's the same number that's in my denominator. If I leave them the same, they cancel out because they both mean 10 times 9 times 8 times 7, da 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 da, right? So if I have that in the top and the bottom, that's really me canceling each of those out. So instead of writing out that entire problem, I can just stop at that whatever number's in the bottom, that same factorial on the top, and cancel them out because they mean the same thing. So I'm left with 12 times 11, which gives me 132. Now, we know that 12 tenths can reduce down to 6/5 by dividing by 2. So is 12 factorial divided by 10 factorial the same thing as 6 factorial divided by 5 factorial? What can you conclude? Okay. All right. So we know that 12 factorial over 10 factorial is 132 because we just did that problem. Let's see what 6 factorial over 5 factorial is. Well, those cancel out, so I'm just left with 6. So therefore, they are not the same thing. So we can conclude that when dividing 2 factorials, you can't just ignore the factorials and reduce the fractions as usual. Okay? So you still have to work out the factorial. All right, why don't you guys go ahead and pause the video, take a second and practice the last 3 problems on your own, and press play when you're ready for the answer. All right, so now that you've had a second to work those out, you should have gotten 720, 11,880, and 30. Okay, moving on. All right, next up we are talking about permutations. An arrangement of indistinct objects in a very important keyword, specific order is called a permutation of the objects. So when we think about permutations, we are talking about putting objects in a specific order. And the reason why I keep saying that is because when we talk about combinations, it'll be a little different. So you want to know that permutations mean that they have to be in a specific order. First example for permutations. Suppose that a photographer wants to arrange 3 people. We have Carmen, we have Juan, and we have Christina in a specific order for a portrait. List the possible orders. Okay, list the possible orders. Well, let's go ahead and just start listing out the orders. Remember, they have to be in a specific order, meaning that they won't repeat. Let me see. So we can start with Carmen, Juan, Christina. Then we can go Juan, Christina, Juan, Carmen, trying to keep it in some type of order. Christina, do the same thing over and over. And then that leaves us with Christina, Juan, and Carmen. Okay, so we start with Carmen, Juan, Christina. Then we go Juan, and then I go back to the first one, Carmen, Christina. And then I go Christina, Juan, Carmen. Okay. I also can have Carmen, Christina, Juan, Juan, Christina, Carmen, and Christina, Carmen, Juan. Oh, spelled it wrong. Okay. All right. So these are the 6 possibilities that we have. Okay. So it says use the fundamental counting principle to find the number of possible orders and make sure that it matches the answer in part A. Okay, well, there are 3 ways we could choose the person in the first position. After that, there are only 2 left to choose from the second position and just 1 for that last position. So it's the same concept when we were thinking about the lock. Okay, we had 3 the first time. We have all 3 of them. Well, once we use that first person, then we only have 2 people left. And then after that, we only have 1 person left for that third spot. So 3 times 2 times 1 is just 6. Okay, so that's the same concept. That's just 3 factorial because each time we're taking 1 away. We're taking 1 person away. Part C says, how many orders do you think there will be for 8 people? Okay, well, if there are 8 people, listen to order orders will be a lot of work. So we can use the same idea that we use with the fundamental counting principle. And if we have 8 choices for the first position, that next position will only have 7. That next one, 6, 5, 4, 3, 2, 1. In other words, we have 8 factorial, just like here we had 3 factorial for 3 people. And then 8 factorial actually gives us 40,320. Okay, hope everyone is hanging on so far. Okay. All right, so permutations of n objects, the number of permutations of n distinct objects using all of the objects is n factorial. That's pretty much what we just figured out, okay? We listed it with words, and then we wrote the numbers out, and then we concluded that writing those numbers out are the same thing as just making it into factorials. And that's what this is telling us here. So example 5 says calculating the number of permutations. So there are 7 horses in a race in a large jackpot for anyone who can pick the finishing order of all 7 exactly right. How difficult is that? Find the number of possible orders that they can finish. Well, the number of ways, this is pretty much saying the number of ways to order 7 objects. And because it's a race, they're going to be in specific order. Someone has to be in first or second, third, so on and so forth. So this is a permutation problem because we're interested in that number of ways. In other words, we can say 7 factorial, 7, 6, 5, 4, 3, 2, 1, which gives us 5,040. Okay, there are 5,040 possible finishing orders. All right, another example. How many different ways can a pledged class with 20 members choose a president, vice president, and a Greek council representative? No pledge can hold 2 offices. Okay, no pledge can hold 2 offices. Well, we have 20 members total, but we only have 3 positions. We have the president, the vice president, and the Greek council. So the first time, all 20 members have an option. The second time, only 19 of those members have an option. And for the third position, only 18 of those members have an option. So in this way, all we have to do is multiply, and we get 20 times 19 times 18, and that's 6,840 ways. Okay, so notice this one didn't go all the way down to 1 because we were looking for those 3 specific positions to sign those 3 offices. All right. So what happens when we have to take a certain number at a time? So the arrangement of n objects in a specific order, permutation, using r of those objects without replacement is called permutation of n objects taken r at a time. It is written as NPR, but make sure you know that the N and the R are smaller than the P. And it's calculated using this formula. Okay. All right, so write that formula down, highlight it. We're going to use it a lot. And I'll show you how it makes sense. N is the number of objects, and let's write that down. And R is how many they're taken at a time. So example 7 says, in a lottery game, 40 numbered ping pong balls are put in a bin and 4 are chosen at random, 1 at a time. To win the game, players need to match all 4 in the order in which they are drawn. How many different winning orders are there? Okay. All right, so this is a permutation problem because 4 balls are picked from 40 with no repetition. Okay, it's no repetition, so we can use this formula. So the way we would set it up, 40 is the number of objects, and how many do we need? Now this one, I know we just said taken at a time. It's 4 are chosen at random. It says 1 at a time, but this number is actually 4 because they're picking 1 at a time, but we're picking a total of 4 objects. So maybe I shouldn't put taken at a time, but maybe just taken or chosen objects. Okay. All right. So now I'm going to plug those numbers in. So in this case, I have 40 factorial over 40 minus 4 factorial. Start over here. 40 factorial, 40 minus 4 is 36 factorial. So this is where cutting it down comes in handy. 38, 37, 36 factorial. That 36 can cancel with this 36, leaving just those top numbers that we need to multiply. Punch those into your calculator, and you get 2,193,360. Okay, so and this is the lottery that everyone plays. So this is what happens. These are the different winning orders that you can have. Oh my goodness, 2,193,360 different winning orders. So, all right, permutation rule when objects are alike. So this is a little different. The number of permutations of n objects in which k1 objects are alike, k2 objects are alike, etc. is n factorial, and then we have each object, and then you can see the little factorial sign after that. Object factorial. Okay. So let's look at how we can use this in an example. How many different passwords can be made using all of the letters in the word Mississippi? Mississippi. Okay, so the letters can be rearranged. We're going to start by rearranging them. So we have M, we have one M, we have 4 I's, we have 4 S's, and then we have 2 P's. So those are the letters in the word. So that means we have a total 1, 4, 8, 11, a total of 11 letters. We can say our K1, we have 1 M. We can say our K2, we have 4 I's. We can say our K3, we have 4 S's. And we can say our K4, we have 2 P's. Okay, so remember we need the factorial of each of these. So our problem will be set up using this formula, n factorial, which is 11 factorial, over 1 factorial times 4 factorial times, remember this is multiplication. We don't see any symbol, so it's a multiplication, times 2 factorial. Work that out. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. 1 factorial. I'm going to keep 1. Oh, let me not do that. I want to get rid of the factorial symbol. 1 factorial is 1. 4 factorial, I can cancel one of those out. So I'm going to write it, but I'm going to cancel it out. But I still have that other 4 factorial, so that one will be 4 times 3 times 2 times 1. Then I have 2 factorial, which is just times 2 times 1. Punch that in my calculator. 11 times 10 times 9 times 8 times 7 times 6 times 5. And then that's one big number. Divide it. Let's write it down. 1663200. Divided by, what's this? 12 times 2 is 24 times 2 is 48. Divided by 48, which gives us 34,650 different passwords. All right. Give that a second to sink in. Once again, as this is a video, you can stop and pause and rewind it and look at it again as many times as you need to. But this does bring us to the end of this section where you have your discussion questions that you can read over. Make sure you're writing down any questions or comments or concerns that you have about this section and emailing them to me as soon as you can.